In 2025, NASA's Curiosity rover made a discovery that has left scientists both fascinated and unsettled. While examining Martian soil, Curiosity detected complex carbon-based molecules, specifically long-chain hydrocarbons. What's particularly shocking is that these molecular structures closely resemble organic substances found almost exclusively in Earth's biosphere. This kind of chemistry is rare, even in our own solar system. The molecules detected are not just chemical curiosities. Their presence may point to something far more significant. Some experts worry they could be evidence of Earth-based contamination, while others suggest they might indicate a deeper, stranger truth, perhaps even signs of life, or at least biology-like processes on Mars. The implications of this finding are monumental. If proven to be genuinely Martian in origin, this discovery could upend decades of planetary science. It might force a complete re-evaluation of all previous data collected from the red planet. NASA's approach to exploring Mars, from sampling techniques to planetary protection protocols, could be fundamentally altered. The molecules detected, specifically decane, undecane, and dodecane, were found in mudstone from what is believed to be an ancient lakebed, a location long thought to be a possible cradle of past Martian life. What's troubling is how closely these hydrocarbons resemble biological signatures typically produced by life on Earth. This raises two stark possibilities. Either life, or something like it, once existed on Mars, or we accidentally brought these chemical markers there ourselves. To understand how that might have happened, we have to consider the history of contamination risks. Despite the intense sterilization protocols NASA employs when building spacecraft, total sterilization is nearly impossible. In a study of NASA's so-called clean rooms, the facilities where spacecraft are assembled, scientists found 215 bacterial strains. Even more surprising, 26 of those strains were completely new to science, previously undiscovered organisms. These microbes weren't just surviving, they were thriving in these ultra-clean environments, and they had evolved traits that made them incredibly tough: resistance to radiation, the ability to survive vacuum conditions, and adaptations for withstanding UV exposure. These are exactly the qualities a microbe would need to endure a journey to Mars. Some of these bacteria were found on parts of spacecraft bound for the red planet, raising serious concerns about contamination. Even with advanced cleaning methods like alcohol wipes, hydrogen peroxide vapor treatments, and heat sterilization, some microbes appear to be too robust to eliminate entirely. If any of these microbial stowaways did survive the trip, they could now be influencing what we're detecting in Martian soil. What makes matters worse is a documented mistake during Curiosity's mission. A drill bit, an essential tool for collecting soil samples, was attached to the rover late in its preparation, after the main sterilization processes had been completed. NASA confirmed this deviation from protocol, stating that while the drill bit still met basic safety standards, it hadn't undergone the full decontamination regimen. And it was this very drill bit that was later used to extract the samples where these unusual hydrocarbons were discovered. This procedural slip introduces real uncertainty into the findings. If Earth microbes or molecules made their way to Mars, via that drill bit, they could now be influencing the very samples scientists are studying. To address these risks, NASA has implemented advanced contamination monitoring tools. The Perseverance rover, for example, carries witness tubes, sealed containers filled with inert material. These tubes remain untouched during the mission and are later opened only to detect any potential contamination from the rover itself. If any Earth-based organics are found in these witness tubes, it would strongly indicate that similar compounds detected in Martian soil might have come from Earth. Curiosity, which launched earlier, uses another method, known as blank organics. These are Earth-based control samples analyzed alongside Martian ones to help scientists identify any patterns that may suggest contamination. The results of these control analyses are still being processed, and the scientific community is anxiously awaiting them. If the molecular patterns in the control samples match those from Mars, Earth contamination becomes a likely culprit. If not, the case for indigenous Martian organics grows stronger. Yet this entire issue is made more complex by the fact that organic molecules produced by life tend to look similar, regardless of their origin. Carbon-based life, whether on Earth or elsewhere, often generates comparable chemical signatures. This makes the job of astrobiologists even harder, distinguishing between true Martian biology and highly adaptable Earth microbes that have evolved in a new environment. That evolution isn't just hypothetical. Studies from the International Space Station show that microbes can adapt quickly when exposed to space. Some strains altered their behavior, gene expression, and even resistance to stress after spending time in orbit. If Earth microbes did survive the trip to Mars, they may have already started to change. Over time, these changes could become so significant that the microbes look like an entirely new form of life, creating a false positive for scientists searching for extraterrestrial biology. And this is perhaps the most chilling scenario, that we discover life on Mars, celebrate the breakthrough, only to later realize that what we found were simply Earth microbes, evolved under Martian conditions. Such a mistake wouldn't just be embarrassing, it would shake public confidence in space science and could jeopardize future missions. Worse still, even detailed genetic testing might not immediately reveal the truth if the microbes have diverged enough from their Earth ancestors. Another piece of this puzzle is methane, an elusive gas that's been appearing in Mars's atmosphere since 2013. Curiosity has detected sudden spikes of methane levels that vanish just as quickly as they appear. On Earth, most methane in the atmosphere is produced by living organisms, but on Mars, its presence is difficult to explain. The gas should break down quickly under Martian UV radiation, meaning there must be an active source replenishing it. That source could be geological, such as chemical reactions in rocks interacting with water, or it could be biological. Adding to the complexity is NASA's cautious approach to potential water sites on Mars. Strange dark streaks, known as recurring slope lineae (RSLs), have been observed on Martian hillsides. These features seem to appear during warmer seasons and fade in colder ones, possibly indicating seasonal flows of salty water. You'd think NASA would want to send rovers straight there, but instead they've avoided these regions entirely. The reason? Fear of contamination. If Earth microbes have already hitched a ride to Mars, sending them to areas that might host liquid water is a massive risk. Water is essential for life, and if our microbes land in a wet Martian environment, they might survive or even begin to spread. This dilemma highlights a cruel irony. We're searching for life on Mars while also trying not to introduce it ourselves. In attempting to avoid contamination, NASA follows a principle of planetary protection. Better to delay a discovery than to damage or erase evidence of native life. But it may already be too late, so we're left with an enormous challenge. Are the hydrocarbons and methane we're detecting products of ancient Martian biology, or just the biological footprints of Earth microbes we accidentally delivered? The possibility of a false positive, where we mistake Earth life for Martian life, is the central scientific concern. And until we can definitively separate Earth-based contamination from native Martian chemistry, every discovery remains under a cloud of uncertainty. As investigations continue, the next phase of analysis, particularly the results from witness tubes and organic control samples, will be crucial. If Earth is the source, we'll have to rethink everything. But if it's not, then we may be standing at the edge of one of the greatest discoveries in human history.